Every major space agency on Earth is actively searching for signs of alien life. We have radio telescopes scanning millions of stars. We have satellites analysing the atmospheres of distant planets. We have probes crawling across the surface of Mars looking for ancient microbes. We've been doing this for over 60 years, and we've found nothing. Not a single confirmed signal. Not one piece of biological evidence. Not one radio transmission we can't explain. By the end of tonight, you're going to understand why that silence might be the most important data point in the history of science, and why the most likely explanations for it are things nobody wants to say out loud. Here's what most people think the situation is. We haven't found aliens yet because space is big and we haven't looked long enough. Given enough time, given better telescopes, given more patience, we'll eventually pick up a signal from somewhere out there. The universe is vast, we're young, we just need to keep looking. That framing is wrong, not incomplete, not oversimplified. Wrong in a way that matters, because it lets us off the hook from confronting something far more uncomfortable. The size of the universe is not why we haven't found aliens. We have found nothing, despite searching in exactly the conditions where we should have found something by now. The silence isn't a symptom of insufficient looking. It's a symptom of something deeper. And the moment you actually run the numbers, the moment you sit down with what we know about how common planets are, how old the galaxy is, how much time intelligent life has had to spread, the silence stops being a puzzle and starts being a warning. Let's build this from the ground up, because you need to understand the scale of the problem before you can understand why the silence is so strange. The Milky Way contains somewhere between 200 and 400 billion stars. The Kepler Space Telescope, which spent 9 years staring at a small patch of sky and counting planetary transits, told us that roughly every star has at least one planet orbiting it. That means somewhere between 200 and 400 billion planetary systems in our galaxy alone. Of those, estimates suggest around 40 billion planets orbit in what astronomers call the habitable zone, the region around a star where liquid water could exist on a planet's surface. 40 billion in our galaxy. Not the observable universe, our galaxy. Now here's where the timeline becomes the issue. The Milky Way is approximately 13.6 billion years old. Our Sun formed about 4.6 billion years ago. That means the galaxy had been producing stars, and therefore planets, for about 9 billion years before our Sun lit up. Some of those older stars have planets that are billions of years more ancient than Earth. If life emerged on those planets, at roughly the rate it emerged here, and we have no strong reason to think Earth is uniquely fast, then intelligent civilizations could have arisen billions of years before us. Not thousands, not millions, billions. And here is the part that should stop you cold. A civilization with just a 1 million year head start on us, a civilization that emerged 1 million years before humans did, which is a blink of an eye on a 9 billion year canvas, would have had time to colonize every star in the Milky Way. Even at a fraction of the speed of light, even spreading slowly from star to star with long pauses between jumps, a civilization that began expanding 1 million years ago could have reached every corner of this galaxy by now. The math is straightforward. If you expand outward at even 1% of the speed of light, you cross the diameter of the Milky Way in about 10 million years. That's less than 0.1% of the galaxy's age. They should be everywhere. They're not. This is the Fermi Paradox, named for physicist Enrico Fermi, who reportedly asked the question during a lunch conversation in 1950. If the universe is so old and so large, and planets are so common, and life seems to emerge relatively easily, where is everybody? The question has been sitting there for 75 years. We have not answered it. We have proposed dozens of possible answers, some of which I'll go through tonight, but no confirmed answer. And that fact, that we have no confirmed answer, is itself significant, because the silence is not the absence of something. It is the presence of something, a constraint, a law perhaps, something that is preventing the galaxy from filling up with detectable civilizations. And the question of what that something is may be the most important question our species has ever asked. The first category of explanations is what you might call the "they're out there, we just can't see them" family. These are the comfortable answers, the ones that don't require us to change how we think about our place in the universe. Maybe they're using communication methods we're not looking for. We search primarily in radio wavelengths because radio is what we use. But a civilization a million years more advanced than us might have moved past radio the same way we move past smoke signals. Maybe they communicate with neutrinos, which pass through matter almost without interaction, and could carry signals through the entire galaxy without any loss. Maybe they use modulated gravitational waves. Maybe they use some phenomenon we haven't discovered yet, some physics we don't have access to, some communication channel that is to radio what radio is to two tin cans on a string. If that's true, we wouldn't detect them no matter how many radio telescopes we pointed at the sky. This explanation is possible. It is not satisfying because it doesn't actually solve the problem. Even if advanced civilizations don't broadcast in radio, they would still produce effects we could detect. A civilization large enough to have colonized multiple star systems would be using enormous amounts of energy. Energy use produces waste heat. Waste heat radiates as infrared. We can look for stars with anomalous infrared signatures, stars surrounded by structures that are absorbing too much light and re-emitting it as heat. We've looked. The surveys have been done. We've found some interesting candidates, including a star called KIC 8,462,852, nicknamed Tabby Star, that shows irregular dimming patterns unlike anything a transiting planet would produce. But every candidate, when followed up closely enough, has had a more mundane explanation. So, different communication technology doesn't get us out of the problem, because a sufficiently advanced civilization would be thermodynamically detectable, even if it's radio silent. Maybe they exist, but they're deliberately hiding. This is the zoo hypothesis, proposed by radio astronomer John Ball in 1973. Earth is a nature reserve. We're being observed, studied, perhaps protected from contact until we reach some threshold of maturity. I want to be honest about this one. It cannot be ruled out. It is also the most anthropocentric, most wishful, and least falsifiable explanation on the list. It requires every advanced civilization in the galaxy, every one of them, to have agreed on and enforced a policy of non-contact. All it takes is one civilization, one rogue faction, one artificial intelligence that decides the policy is wrong, one probe sent by a dead civilization that kept running after its creators were gone. One exception breaks the hypothesis. A probability that every civilization in a galaxy this old maintains perfect silence is not zero, but it is very small. And it requires a coordinated galactic consensus among beings we have never contacted and cannot verify. It is, in other words, an explanation that can explain anything, which means it explains nothing. Maybe the signals exist, but we've missed them. Our SETI searchers have covered a tiny fraction of the possible parameter space. We've listened to a small number of stars in a narrow range of frequencies for a brief period of time. The WOW signal, detected in 1977 by the Big Ear radio telescope at Ohio State University, remains the most famous unexplained candidate, a 72-second burst of radio energy at 1420 MHz, the frequency of hydrogen emission. The frequency SETI researchers had specifically flagged as the most logical choice for interstellar communication. It was 30 times stronger than the background noise. The astronomer on duty circled it on the printout and wrote "wow" in the margin. It was never detected again, despite repeated searches. It could have been a natural source we don't understand. It could have been a one-time transmission. We don't know. But the fact that it appeared exactly where we were looking, at exactly the frequency we predicted would be used, and then never repeated, is either extraordinary coincidence or evidence of something frustratingly just beyond our grasp. The missing signals argument has some merit, but it too doesn't fully resolve the paradox, because even granting that we've searched only a small volume of possibility space, the absence of macro-scale evidence is harder to explain away. We see no Dyson spheres, megastructures surrounding stars to capture their total energy output. We see no evidence of stellar engineering. We see no galaxy-spanning communication networks lighting up the radio sky. The absence isn't just in our narrow search, it's in the gross, obvious, hard-to-miss signatures of any civilization operating at scales we would expect after millions of years of expansion. So, the comfortable explanations have holes, which brings us to the uncomfortable ones. The Great Filter is the name given to whatever is preventing the galaxy from filling up with detectable civilizations. The concept was formalized by economist Robin Hainson in a 1998 paper, and it is, in my view, the most important piece of analysis that has come out of the Fermi Paradox discussion. The argument goes like this: somewhere on the path between dead chemistry and galaxy colonizing civilization, there is a step, or possibly multiple steps, that is so unlikely, so difficult, that almost nothing makes it through. The galaxy looks empty because the filter stops civilizations before they get big enough to see. The critical question is, where is the filter relative to us? There are two possibilities, and their implications are almost perfectly opposite in terms of what they mean for humanity's future. The first possibility is that the filter is behind us, that we have already passed through it, that whatever the hard step is, the emergence of life from chemistry, the development of complex cells, the evolution of multicellular organisms, the emergence of intelligence, something else entirely, we already survived it. We're on the other side. We made it. And the galaxy looks empty, not because civilization inevitably destroys itself, but because getting to where we are is extraordinarily rare. We're one of the very few who made it through the needle's eye. The second possibility is that the filter is ahead of us, that the hard step is something civilizations face after they develop technology, after they discover nuclear fission, after they build artificial intelligence, after they start engineering biology, after they do what we are doing right now in the early 21st century. That the galaxy looks empty because every civilization that gets to our level of development hits a wall, and almost none of them survive it. These two possibilities lead to completely different conclusions about what we should be doing and how worried we should be about our own future. And figuring out which one is true may be the most urgent scientific and philosophical project of our time. Let's talk about what the filter might be, if it's behind us. What could be rare enough, difficult enough, that it explains the emptiness of the galaxy? The emergence of life itself is the most obvious candidate. We don't know how life began. We have theories. We have laboratory experiments showing that amino acids form naturally under simulated Earth conditions. We have evidence that the building blocks of life, complex organic molecules, exist throughout the universe, in interstellar gas clouds, in meteorites, on comets. We even have evidence that the chemistry of life is not exotic. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, common elements, ubiquitous chemistry. But building blocks are not life. The gap between a collection of organic molecules and a self-replicating system capable of Darwinian evolution, a system that can copy itself, make errors in copying, and be selected based on how well those variants function, is enormous. We don't know how that gap was crossed. We have no replicated laboratory experiment that starts with chemistry and ends with life. The origin of life is one of the deepest unsolved problems in science. And if that transition is extraordinarily rare, if it requires a combination of conditions so specific that it happens only once per galaxy per billion years, then the emptiness of the galaxy is explained without requiring any future catastrophe. Life exists here. We are the lucky exception. This explanation becomes less satisfying when you consider how quickly life appeared on Earth. The planet formed about 4.6 billion years ago. The surface was molten for the first several hundred million years. By 3.7 billion years ago, possibly earlier, there is evidence of life in the rock record. Life appeared within a few hundred million years of the surface becoming habitable. That's fast. If life were extraordinarily rare, you'd expect it to take longer on a planet where conditions are right. The quickness of life's appearance here suggests either that life emerges easily whenever conditions allow, or that we are subject to a profound selection effect. We can only be having this conversation on a planet where life emerged. So of course, it looks like it happened quickly. The second candidate for a past filter is the development of complex cells, specifically the eukaryotic cell, the type of cell that makes up every plant, animal, and fungus on Earth. Eukaryotic cells are fundamentally different from bacteria and archaea. They have a nucleus, they have mitochondria, organelles that generate energy for the cell, they have an elaborate internal machinery that simple cells lack. And as far as we can tell, the eukaryotic cell arose exactly once in the history of Earth, about 2 billion years ago, to an event called undul symbiosis. One simple cell engulfed another simple cell, and instead of digesting it, the two formed a permanent partnership. The engulfed cell became the mitochondrion. This single event was the prerequisite for all complex life on Earth. Every multicellular organism, every animal, every plant, every fungus traces its ancestry to that one unlikely merger. It happened once in 4 billion years of life on Earth. If that event is the filter, if that one-time fusion is what's extraordinarily rare, then the galaxy could be full of planets covered in bacteria and essentially empty of complex life. Microbial life everywhere, intelligent life almost nowhere. The third candidate is the evolution of intelligence itself. Complex multicellular life has existed on Earth for about 600 million years. Intelligent tool-using life has existed for perhaps a few million years. Technological civilization has existed for a few thousand. Intelligence capable of interstellar communication has existed for less than a century. On the billion-year timescale of animal evolution, technological intelligence is so recent it barely registers. And looking at the history of animal life, intelligence seems like one solution among many, not an inevitable outcome, not a guaranteed destination. But one particular evolutionary path taken by one particular lineage under one particular set of circumstances. Dolphins are intelligent, but lack the limbs to build technology. Crows solve complex problems, but live in a world that doesn't reward the accumulation of technological knowledge across generations. Octopuses are extraordinarily smart, with distributed nervous systems unlike anything in vertebrate evolution. But they live short lives and have no persistent culture. Intelligence evolved multiple times on Earth, in different lineages, in different forms. But the specific combination, sufficient intelligence, social structure, long enough lifespan, the right physical body for tool use, a stable enough environment for culture to accumulate across generations, may be rare. Maybe it's happened a handful of times in the galaxy. Maybe it happened once. All of these past filter candidates have something in common. They're reassuring. If the filter is behind us, our future is open. We made it through the hard part. The road ahead, while not without challenges, isn't subject to a near-universal kill switch. We can aspire to longevity, expansion, the gradual accumulation of knowledge and capability across deep time. But the second family of explanations, the ones where the filter is ahead of us, is where the real darkness lives. And I want to spend serious time on this, because the evidence here is not comfortable, and it doesn't deserve to be made comfortable. If civilizations typically destroy themselves after reaching a certain technological threshold, that threshold might be exactly where we are now. Let me walk you through what that would look like as a pattern in the galaxy. Imagine a galaxy with millions of planets, where life emerges and evolves over billions of years. On each of those planets, civilizations arise. They discover physics, they harness energy, they develop chemistry and biology as sciences. They build communication technology. They begin to have the capability to detect and contact other civilizations. And then, within a few hundred years of reaching that capability, they disappear. Not gradually, not slowly, but within a window so brief relative to cosmic time that it's essentially instantaneous. The civilization lights up and goes dark before the ripples of its existence have time to cross the galaxy. If that's what's happening, the galaxy would look exactly as it does. Quiet, dark, punctuated by brief flickers that we can't quite catch because our own brief flicker only started a century ago. What could cause such consistent, reliable self-destruction? The candidates are not abstract. They are things we have already invented, things we are already doing, things that are already in progress. Nuclear weapons are the most obvious. We invented them in 1945. By 1986, at the peak of the Cold War, the combined nuclear arsenals of the United States and Soviet Union contained more than 60,000 warheads, enough to destroy every major city on Earth many times over. We came extraordinarily close to using them. The Cuban Missile Crisis in October 1962 is the most documented near miss, but declassified records from both sides reveal a string of incidents where nuclear war was prevented by individual decisions made under imperfect information. In 1983, Soviet Lieutenant Colonel Stanislav Petrov decided, against protocol, not to report a warning signal indicating incoming American missiles. The warning was a false alarm caused by a satellite malfunction. If Petrov had followed procedure, the Soviet response might have been launch. We don't know, but he didn't follow procedure. He made a judgment call. We're here because one man on one night made the right call. That is not a comfortable margin. One person, one night, one decision. And Petrov's case is not unique. In 1995, Russian radar systems detected a missile launch originating from Norway, actually a scientific rocket launched by Norwegian and American researchers to study the Northern Lights, which had been announced to Russian authorities weeks in advance, but whose notification had apparently not reached the right people. President Boris Yeltsin was presented with the nuclear briefcase for the first and only time in the post-Soviet era. He had minutes to decide whether to launch a retaliatory strike. He waited. The missile flew its course without triggering any secondary signals. The briefcase was closed. The crisis passed in less than 10 minutes and was never publicly acknowledged for years afterwards. We are building a historical record of close calls that should alarm us. Every decade of the nuclear era contains at least one documented incident where the difference between global catastrophe and continuation was a single person's decision. A malfunctioning sensor, a miscommunication between agencies, or a piece of protocol not followed. The probability of nuclear war in any given year is small, but we have been in the nuclear age for less than 80 years. Small annual probabilities, compounded across centuries, accumulate towards certainty. If a civilization like ours sustains nuclear arsenals for 1,000 years without using them, that requires an unbroken chain of correct decisions across dozens of generations, under conditions of political instability, technological change, and the gradual proliferation of weapons to new actors. That is a very long chain. Long chains break. The nuclear arsenal has shrunk since the Cold War peak, from roughly 70,000 warheads to roughly 12,000. But 12,000 is still far more than enough to end industrial civilization. And the treaty architecture that constrained the US-Soviet competition has been deteriorating. The Intermediate Range Nuclear Forces Treaty was abandoned in 2019. The Open Skies Treaty collapsed in 2020 and 2021. New START, the last major arms control treaty between the United States and Russia, was suspended by Russia in 2023. The world currently has more nuclear-armed states than at any point during the Cold War, 9 countries, with more potentially on the threshold, and no overarching framework for managing the risk that any of them uses what they have. Climate change is slower, but in some ways more certain, precisely because it operates through mechanisms that do not require any single bad decision. It requires only continuation of current behaviour. We have been adding carbon dioxide to the atmosphere at an accelerating rate for over a century. The concentration of carbon dioxide is now above 420 parts per million, higher than at any point in at least the past 3 million years, a period that includes multiple ice ages and warm periods, but not anything close to what we're currently producing. The planet is warming at a rate faster than any natural climate change in the geological record since the asteroid impact that ended the Cretaceous. We know this. We have known it for decades. The political and economic response to this knowledge has been inadequate by any reasonable measure. Global emissions today are higher than they were when the first major international climate agreement, the Kyoto Protocol, was signed in 1997. The Paris Agreement of 2015 set targets that, if fully implemented by every signatory, would still result in warming above 2 degrees Celsius relative to the pre-industrial baseline, which is the threshold above which the risk of triggering self-reinforcing feedback loops increases substantially. Not all signatories are on track to meet their targets. Some have withdrawn and rejoined. The gap between the scientific consensus on what is necessary and the political consensus on what is achievable has not narrowed. It has widened. The great filter version of the climate story isn't that climate change kills everyone. It's subtler and probably worse. Climate change destabilizes. It creates resource scarcity, particularly water and arable land. Resource scarcity creates conflict. Conflict between states with nuclear weapons escalates differently than conflict between states without them. The chain of causation from climate disruption to existential catastrophe runs through political systems that are already under stress from inequality, democratic backsliding, and the information disruptions caused by social media. The mechanisms reinforce each other in ways that are difficult to model, but easy to see in retrospect. A civilization that fails to coordinate a response to a predictable environmental catastrophe it created itself is exhibiting exactly the kind of coordination failure that would also prevent it from navigating the other risks on this list. The failure mode is not stupidity. We understand the problem. It's the structural inability of competitive nation-states to make collectively rational decisions when those decisions require near-term costs for long-term diffuse benefits. That structural failure, that gap between what individuals and nations optimize for and what the species needs, is itself a candidate filter. A species that develops the technology to alter its planet's climate before developing the institutional capacity to manage that alteration is in a dangerous situation. We are that species. Artificial intelligence is newer and in some ways more uncertain. We don't know what happens when you build a system that is smarter than you. We have never done it. We are working toward it. The timeline is disputed. Estimates range from decades to centuries, but the direction is not disputed. We are building systems that are increasingly capable, increasingly autonomous, increasingly integrated into critical infrastructure. The question of how to ensure that these systems, as they become more capable, remain aligned with human values and human survival is genuinely unsolved. Not we're making progress toward a solution. Genuinely unsolved in the sense that there is no consensus on whether the problem is even solvable, let alone how to solve it. An artificial intelligence that is substantially smarter than humans and that has goals misaligned with human survival is an existential risk. Not because it would be malicious. Malice requires caring about humans enough to want to harm them. The concern is indifference. A system with a specific objective and the capability to pursue that objective ruthlessly, without the evolutionary and cultural constraints that make humans hesitate before causing harm, is dangerous for the same reason a powerful optimization process is dangerous. It will find solutions that satisfy its objective without satisfying the things you actually care about, but failed to fully specify. There is a subtler version of the AI risk, that doesn't require artificial general intelligence and doesn't require any single catastrophic event. It goes like this. As AI systems become more capable and more integrated into the decision-making processes of governments, militaries, and financial systems, human oversight of those systems decreases. Not because anyone decides to remove oversight, because the systems operate faster than human review allows, because the volume of decisions exceeds human capacity to monitor, because the competitive pressure between states creates incentives to automate and accelerate rather than pause and verify. The risk is not a single AI that turns against humanity. The risk is a gradual erosion of human agency over the systems that determine whether wars start, whether financial systems collapse, whether critical infrastructure fails, until at some point the humans in the loop are not really in the loop anymore, and the systems are operating according to their own local optimization criteria, which may or may not be aligned with human welfare at the global level. This is not science fiction. It is the trajectory we are on. High-frequency trading systems already make decisions in microseconds that move markets in ways no human can track in real time. Military targeting systems already recommend strikes faster than human review processes can evaluate them. The trend is clear. The question of where it ends is not. Engineered biology is another candidate. Biotechnology is advancing rapidly. The tools for editing genomes, CRISPR and its successors, are becoming cheaper, faster, and more accessible every year. The cost of DNA sequencing has dropped faster than Moore's law, faster than the cost of computing for over 2 decades. We approach a small team with modest catalysts to make backgrounds, not a weapon of mass destruction in the traditional sense, something worse, something self-replicating, something that spreads before it's detected, something optimized for transmission rather than detectability. Natural pandemics are constrained by evolutionary pressures that push toward transmissibility over lethality. A pathogen that kills its hosts too quickly doesn't spread well. An engineered pathogen has no such constraint. The COVID-19 pandemic demonstrated, in vivid and painful detail, several things relevant to this risk. First, that a novel respiratory pathogen can spread globally before containment is even seriously attempted. The virus was in dozens of countries before its existence was formally acknowledged. Second, but even wealthy, technologically sophisticated countries with advanced public health systems are unable to mount an adequate early response to a pandemic they were not specifically prepared for. Third, that the social and political dynamics of pandemic response, the politicization of public health measures, the information disruption from social media, the tension between individual freedom and collective safety create enormous friction in exactly the moment when rapid collective action is most needed. COVID-19 killed millions and disrupted global society for years. Its infection fatality rate across all age groups was somewhere below 1%. An engineered pathogen designed for maximum harm could, in principle, combine high transmissibility with a much higher fatality rate. The global surveillance and response infrastructure that would be needed to reliably detect and contain such a threat at its source does not currently exist. Building that infrastructure is technically possible. It is not being prioritized proportionate to the risk. But now I want to discuss the dark forest hypothesis in detail, because it is one of the more disturbing possible explanations for the Fermi Paradox, and because it has implications for our own behavior that deserve serious attention. The dark forest was the central metaphor in a science fiction trilogy by Chinese author Liu Cixin, the Three-Body Problem series, but it is based in a game-theoretic argument that has been analysed seriously by researchers. The argument is as follows. Assume the universe contains multiple civilizations. Assume resources are finite, which they are, even given access to all the matter and energy in the galaxy. Those quantities are finite. Assume that civilizations cannot be certain of each other's intentions, and that the distances and communication delays involved in interstellar contact make establishing trust essentially impossible. Under these conditions, what is the optimal strategy when you detect another civilization? The pessimistic answer is, eliminate it before it can eliminate you. Not because you are hostile, not because the other civilization has done anything to you, but because you cannot verify that it won't become a threat, and because the cost of being wrong, being destroyed by a civilization you could have neutralized, is total and irreversible. The asymmetry of the stakes pushes rational actors toward preemptive elimination. And in a galaxy where this reasoning is universal, the equilibrium is that every civilization stays silent and destroys any signal of another civilization's existence the moment it detects one. The galaxy would be dark and quiet, not because it's empty, but because everyone is hiding and eliminating any light that threatens to expose them. This is a coherent, game-theoretic argument. I want to be honest that I don't think it is likely to be the primary explanation for the Fermi Paradox. The engineering challenges of destroying a civilization from light years away are enormous, and cooperation is in general a more efficient strategy than mutual annihilation when resources are genuinely abundant on galactic scales. But the argument is not obviously wrong. And it has a disturbing implication for our situation. We have been broadcasting our location into the galaxy for over 100 years. Radio signals travel at the speed of light. By now, our signals have reached every star within roughly 100 light years. If the dark forest hypothesis is correct, we have already announced ourselves to any civilization that was listening in that volume of space. We cannot unring that bell. The question of whether we should be actively broadcasting, deliberately sending powerful focused signals toward nearby stars to announce our existence and invite contact, is called METI, Messaging Extraterrestrial Intelligence. It is one of the most genuinely contested questions in the SETI community. The historical position of most SETI researchers was that passive listening was safe, but active broadcasting was potentially dangerous. You don't know who's listening, and you don't know their intentions. Stephen Hawking argued publicly against METI, drawing an analogy to the encounter between the indigenous peoples of the Americas and European colonizers. Contact with a more technologically advanced civilization did not go well for the less advanced one. The counter-argument is that any civilization capable of reaching us would be so far ahead of us technologically that our existence would already be known to them through passive observation of our electromagnetic leakage, and at the marginal risk of deliberate broadcasting is small compared to the potential benefit of making contact. This argument has some merit, but it depends on assumptions about the intentions and capabilities of other civilizations that we cannot verify. And the asymmetry of the stakes, if contact goes badly, it goes very badly, suggests that caution is warranted even at the cost of some potential upside. The METI debate has never been resolved within the scientific community. There is no international protocol governing whether or how to broadcast. Individual researchers and organizations have sent messages. The Arecibo message of 1974, various subsequent transmissions, without global consensus on whether doing so was wise. This lack of coordination is itself an example of the coordination failure I described earlier. We cannot even coordinate a decision about whether to announce ourselves to the galaxy. One of the things that the Fermi Paradox does when you sit with it long enough is reveal the structure of the problem of civilizational coordination at the deepest level. Almost every serious explanation for the silence points back to the same issue: the difficulty of making decisions collectively at the scale of a species under conditions of uncertainty, with different actors having different interests and different time horizons. The filter, in almost every version of the story, is some form of coordination failure. The failure to manage a technology responsibly, the failure to respond to a collective threat, the failure to agree on how to behave toward other civilizations. The filter is not an external obstacle, it is an internal one. This is either deeply discouraging or deeply clarifying, depending on how you look at it. And then we talk about corrected methodology. We are intelligent. The gap between knowing what to do and doing it is not a knowledge problem. It is a governance and incentive problem. And those are much harder. It is clarifying because it tells us where to focus. The most important investments we can make in terms of improving our odds of passing through the filter are not in better physics or better technology. They are in better institutions, better mechanisms for collective decision-making, better ways of aligning the incentives of individual actors, organizations, and states with the long-term interests of the species. The technical civilizational challenges we face are tractable given adequate coordination. The question is whether we can build adequate coordination before the technical challenges overwhelm us. That is not a scientific question. It is a political and social question. And it is the most important question of this century. Now let me address the possibility that is simultaneously the most reassuring and the most strange, that we might actually be first. The universe is 13.8 billion years old. The Milky Way is 13.6 billion years old. But the conditions for complex life as we understand it, rocky planets with liquid water, heavy elements in sufficient quantities for biochemistry, a stable stellar environment, were not present from the beginning. The first generation of stars were massive and short-lived, containing almost no heavy elements. They had to live, fuse elements up the periodic table, and die in supernovae before their processed material could seed the next generation. The heavy element enrichment of the galaxy was a gradual process. The habitable epoch of the Milky Way, the period during which the conditions for complex terrestrial life could exist, began roughly 8 to 10 billion years ago, by most estimates. That's still 4 to 6 billion years before Earth formed. So there is genuine room for civilizations older than ours. But the recent decades of exoplanet research have added a nuance. The most common type of star in the galaxy, red dwarfs, are long-lived but producing tense flare activity in their youth that may be inimical to life on closely orbiting planets. The types of stars most conducive to life, Sun-like G-type stars and slightly cooler K-type stars, are less common and younger on average in their distribution through the galaxy. The peak of habitable planet formation may be more recent than early estimates suggested. Moreover, we may actually be among the first civilizations to reach our current level of capability in this part of the galaxy. Not because we are special, but because we are early. The galaxy is big. It is not uniform. Different regions have different stellar histories, different ages, different levels of heavy element enrichment. In our particular corner, the outer regions of the Milky Way's disk, the history of star formation and heavy element enrichment is such that planets like Earth only became possible within the last 4 or 5 billion years. And complex intelligence on rocky planets may need that long to evolve. We may not be looking for civilizations that had a billion-year head start. We may be among the first wave. If that is true, the Fermi Paradox dissolves, not because civilization is rare, but because we are genuinely early in the cosmic history of intelligence. The silence is the silence of a universe that hasn't gotten there yet. Mostly. A universe in which we are the vanguard, or one of the first ships over the horizon, rather than a latecomer in a galaxy full of ancient elders who inexplicably have not made contact. This interpretation does not resolve the question of whether the filter is ahead of us. Even if we are early, we still face the risks we face. Being first does not make nuclear weapons less dangerous. It doesn't make the alignment problem in AI less difficult. It doesn't make biosecurity less urgent. Being first means the stakes are even higher, because if we are the first species in this part of the galaxy to reach our level of capability, and we fail to navigate the transition safely, we are not just ending our own story. We are foreclosing, perhaps for billions of years, the possibility of complex intelligence in this region of the cosmos. That is a weight worth carrying carefully. Here is the thing about all of these explanations: the past filter, the future filter, the rare earth, the temporal explanation, the zoo, the dark forest. They are not mutually exclusive. The actual answer to the Fermi Paradox may be some combination of several of them operating simultaneously. Life may be moderately rare, perhaps 1 in 1,000 habitable planets develops it. Complex life may be rarer still, perhaps 1 in 1,000 planets with life develops multicellular organisms. Intelligence may be rarer still. And then of the civilizations that do develop technology, perhaps most fail at the coordination challenges before they become interstellar. The product of all these small probabilities may explain why the galaxy is functionally empty at the level of detectable civilizations, without any single explanation bearing the full explanatory weight. The honest answer is, we do not know. We have arguments, we have estimates, we have one data point, ourselves, from which we are trying to infer properties of a distribution that may contain very few members. This is not a situation where the scientific tools we use for other questions are fully adequate. The Fermi Paradox sits at the intersection of astrophysics, biology, game theory, history, and philosophy. No single discipline has the tools to resolve it. What we have is the silence, and the silence is real. 65 years of active searching, including the most sophisticated and comprehensive programs in the history of the effort, have found nothing. Not nothing suspicious that we investigated and ruled out. Some of that exists. Nothing we cannot explain. The null result is robust. And it is telling us something. Exactly what it is telling us we cannot say with certainty, but the range of explanations that fit the data all point in the same direction. Making it to where we are is harder than it looks from the outside. Either getting started is hard, or getting complex is hard, or getting intelligent is hard, or staying around after you get intelligent is hard. One of those things, probably more than one, is a lot harder than the profusion of stars and planets in the observable universe would naively suggest. We are here anyway. We made it to this point. The question is what we do with that. There is a passage in the thinking of the philosopher Derek Parfit that seems relevant here, though Parfit wrote it about something else. He was discussing the nature of personal identity, but the structure of the argument applies. He wrote that what matters is not whether we are the same persons we were in the past, but whether the future will contain persons connected to us in the right ways. By the same logic, what matters about the Fermi Paradox is not whether other civilizations have existed or currently exist elsewhere in the galaxy. What matters is whether the future will contain civilizations connected to what we are building now. Whether the project of intelligence in this part of the cosmos continues, or whether it ends here, in this century, because we could not navigate the technologies we created. That is a question about us, not about them. Not about what happened to the civilizations that came before, or whether those civilizations existed at all. It is a question about whether we can do what, apparently, almost nothing else has managed to do: survive our own capability. The stars are quiet. They have been quiet for a long time, at least as long as we have been listening, and probably much longer. That silence may mean many things, but one of the things it means, almost certainly, is that the path we are on is harder than it appears. That the universe does not hand out longevity to civilizations that develop the ability to destroy themselves. That something, the filter, is working against the persistence of technological species and has been working against it throughout the history of the galaxy. The filter is not in the past for us, or if it is, we cannot be certain of that. The evidence does not allow certainty. What it allows is urgency and clarity, and the recognition that the choices made in this century about nuclear weapons and climate and artificial intelligence and biotechnology, about the institutions we build and the coordination we achieve or fail to achieve, will determine whether the galaxy's silence continues and what that silence ultimately means. The answer is not written yet. The answer is being written now. By us. In real time. In the decisions we make and the ones we fail to make. In the risks we take seriously and the ones we explain away. In the future we build or fail to build. That is an enormous thing to sit with. It should be. The Fermi Paradox is not a puzzle about aliens. It is a mirror. And what it reflects is everything we still have to do. The probability that we are the exception, the civilization that makes it through, is not zero. It may even be reasonably high. But it's not a certainty. And the fact that we are living through the period that, if the great filter is ahead of us, corresponds to the period where civilizations tend to fail, is something worth sitting with, honestly. Here is where I want to spend a moment, on the search for biosignatures, because this is the new frontier of the alien life search, and because it has a specific implication for the great filter argument that most people miss. A biosignature is a detectable chemical or physical signature that indicates the presence of life. On Earth, the most obvious biosignature is oxygen. Our atmosphere is 21% oxygen. That oxygen is produced almost entirely by photosynthesis, by plants, algae, and cyanobacteria. Without living organisms continuously producing it, the oxygen in Earth's atmosphere would react with exposed rock and disappear from the atmosphere on a geological timescale of a few million years. If you detected oxygen in the atmosphere of a distant planet where photosynthesis is not occurring, you would need an explanation. Life is the most parsimonious explanation. The James Webb Space Telescope, launched in December 2021, the most powerful space telescope ever built, has changed the biosignature search in a fundamental way. Its infrared sensitivity and resolution allow it to analyze the atmospheres of exoplanets by a technique called transmission spectroscopy. When a planet passes in front of its star, as seen from Earth, A small fraction of the starlight passes through the planet's atmosphere before reaching our telescopes. Different molecules absorb light at specific wavelengths. By comparing the star's spectrum with the light from the transit, you can determine which molecules are present in the planet's atmosphere. Webb can do this for rocky planets in the habitable zones of nearby stars, a capability that no previous telescope possessed. In 2023, Webb announced the detection of carbon dioxide and water vapor in the atmosphere of TRAPPIST-1c, one of the 7 roughly Earth-sized planets orbiting the nearby red dwarf star TRAPPIST-1, located about 40 light-years from Earth. The detection was a technological milestone, but the interpretation was cautionary. TRAPPIST-1c does not appear to have a thick atmosphere, and the measurements were consistent with a bare rocky world rather than a habitable one. Her announcement illustrated both the power of the new tool and the complexity of interpreting its results. The TRAPPIST-1 system is, for obvious reasons, one of the most intensively studied nearby planetary systems. It has 7 planets, at least 3 of which are in the habitable zone of their host star. The host star is a red dwarf, smaller, cooler, and much longer lived in our Sun, but prone to intense flare activity that could strip atmospheres from closely orbiting planets and irradiate their surfaces with ultraviolet and X-ray radiation. Whether the TRAPPIST-1 planets are habitable depends critically on questions we cannot yet fully answer. Whether they have magnetic fields strong enough to deflect the stellar wind, whether their atmospheres have survived billions of years of flare bombardment, whether the tidal locking that likely keeps one face of each planet permanently facing the star creates conditions too extreme for life. Webb observations over the next several years will tell us more about their atmospheres, but full characterization is a decade-scale project. The broader biosignature search is accelerating. The upcoming Habitable Worlds Observatory, a large aperture UV optical infrared space telescope that NASA has identified as its highest priority large mission in its 2020 decadal survey, is designed specifically to image Earth-like exoplanets, analyze their atmospheres for biosignatures. If funded and built on the anticipated timeline, it could be operational in the 2040s. It would be capable of directly imaging potentially habitable rocky worlds around nearby Sun-like stars and characterizing their atmospheres in detail, looking for oxygen, ozone, methane, water vapor, and the specific combinations of molecules that would indicate a biosphere. If that telescope finds biosignatures on a nearby exoplanet, if it finds oxygen and methane in quantities and combination that suggest active biological production, that will be the most important scientific discovery in human history. It will confirm that life exists beyond Earth. It will tell us that the emergence of life is not unique to our planet. And as I said earlier, depending on how you think about the Great Filter, it may simultaneously be bad news for our long-term prospects as a civilization. The detection of life beyond Earth means that life getting started is not the filter. The filter is downstream of life. It's somewhere on the path between alive and interstellar. And we are on that path. There is a question that rarely gets asked explicitly in these discussions, but which I think is the most important one. What should we actually do, given the uncertainty? The Great Filter hypothesis does not give us certainty about our fate. It gives us a prior, a reason to take existential risks more seriously than we would otherwise. The appropriate response to that prior is not panic. It is not paralysis. It is not the conclusion that because we might fail, we should stop trying. The appropriate response is exactly the opposite. To take the risks seriously enough, to resource them adequately, to build the institutions capable of managing them, to stop treating civilizational scale challenges as second-order concerns relative to whatever the short-term political and economic incentives of the day happen to be. Concretely, this means several things. Nuclear risk reduction is the most urgent because the failure mode is the fastest. Billions of people could die within hours of a decision made by one or a small number of people. The priority should be reducing the number of warheads, bringing new nuclear states into arms control frameworks, extending the treaty architecture that has been eroding, developing verification and confidence-building measures that reduce the probability of accidental launch, and investing in crisis communication infrastructure that reduces the probability of misunderstanding during periods of tension. These are not new ideas. They are ideas that have been systematically underfunded and deprioritized relative to their importance for decades. Climate stabilization is urgent because the consequences of delayed action compound exponentially. Every decade of delay narrows the range of achievable outcomes. The priority should be decarbonizing energy systems as fast as economically feasible, investing in carbon removal technology, building the international coordination mechanisms that allow developing countries to skip fossil fuel infrastructure and develop directly to clean energy, and preparing adaptation infrastructure for the warming that is already locked in. Again, not new ideas that have been inadequately funded and inadequately prioritized. AI safety research is urgent because the pace of capability development is accelerating faster than the pace of safety research. The organizations in governments deploying increasingly capable AI systems have strong competitive incentives to move fast and weak incentives to be careful. Building regulatory frameworks, investing in interpretability and alignment research, establishing international norms around the development of advanced AI systems. These are projects that require both technical work and governance work, and both are currently under-resourced relative to the capability development they are trying to keep pace with. Biosecurity requires building global disease surveillance infrastructure, strengthening international agreements governing dangerous pathogen research, investing in platform technologies that can produce vaccines and therapeutics rapidly against novel threats, and developing detection systems capable of identifying engineered pathogens at their source before they spread. The COVID-19 pandemic demonstrated that we have the scientific capability to respond to novel biological threats. Vaccines were developed in under a year, but lack the institutional infrastructure to do so quickly enough to prevent widespread harm. Beyond these specific priorities, the meta-priority is building the capacity for civilizational coordination itself. The filter, in most versions, is a coordination failure. The appropriate response to a coordination failure is building better coordination mechanisms. This means international institutions with genuine authority and enforcement capacity, not just advisory roles. It means democratic reforms that extend planning horizons beyond electoral cycles. It means educational investment and the kind of long-term, probabilistic reasoning that the current political environment consistently fails to reward. It means cultural investment in the understanding that what happens to the species matters and is not separable from what happens to individual nations and individuals. These are large, difficult, long-term projects. They are exactly the kind of projects that coordination-failing civilizations fail to prioritize, which is why prioritizing them is itself a signal of whether we are the kind of civilization that can navigate the filter. I want to close with something that I think is true and that I don't hear said enough. The Fermi Paradox is frequently framed as a question about aliens. Where are they? Why haven't we heard from them? What happened to them? These are legitimate questions, but the Fermi Paradox is, at its deepest level, a question about us. What it tells us, what the 65 years of silence, combined with everything we know about how common stars and planets are, combined with everything we know about how the galaxy should look if civilizations routinely survived and expanded, is that we are at an extraordinary juncture. Not because we are special, not because we are chosen, because we are here. Because we are the ones who have to decide what happens next. Every civilization that reached our level of capability faced versions of the choices we are facing. Most of them, if the silence is any guide, did not navigate those choices successfully. They hit the filter, whatever it was, and it stopped them. We don't have to be stopped. That is not guaranteed. It is not even likely in the statistical sense of what the galaxy's silence implies. But it is possible. And the fact that it is possible, that we can look at the evidence, understand the risks, build better institutions, make different choices than whatever came before us, is itself an extraordinary thing. It is the thing that makes this moment matter. The stars are on its better than men. They've been quiet for a long time. The question is whether that quietness ends with us, because we added our voice to the galaxy, because we made it through, or because of us, because we became another data point in the silence. The answer is not written yet. The answer is being written now, by us, in the decisions we make and the ones we postpone, in the risks we take seriously and the ones we explain away, in the future we build or fail to build. That is everything. That is what the Fermi Paradox is actually about. If we discovered microbial life on Mars, or in the subsurface ocean of Europa, or in the atmosphere of Venus, we would have established that life emerges independently in our solar system. That it doesn't require the specific conditions of Earth. That it is, at some level, a natural outcome of chemistry, given sufficient time and the right raw materials. That would be extraordinary. It would transform biology, philosophy, religion, our entire understanding of our place in the universe. And it would tell us that the filter is not in the emergence of life. Life isn't the rare step. Life gets through, which means the filter is something that happens later. Something that happens after life emerges, after it evolves complexity, after it becomes intelligent and technological, which means the filter is still ahead of us. By contrast, if we looked everywhere we can look and found nothing, no microbes on Mars, no chemical signatures of life in the outer solar system, no biosignatures in the atmospheres of nearby exoplanets, that would suggest life itself is the filter. The hard step is the beginning. We are extraordinarily lucky to have gotten started at all. And that would be paradoxically the more reassuring finding. Astrobiologist and science communicator Nick Bostrom put this in a single sentence that I find genuinely chilling. If we find that Mars is sterile, that is good news. If we find a Mars covered in microbial life, that would be, in some ways, bad news for humanity. This is what it looks like when science is honest about what the evidence implies. Now, let me give the full picture, because the great filter isn't the only serious explanation, and intellectual honesty requires presenting alternatives fairly. There is a hypothesis called the rare Earth hypothesis, developed by paleontologist Peter Ward and astronomer Donald Brownlee in a 2000 book of the same name. The argument is that the specific conditions required for complex life are extremely uncommon, not just liquid water and the right temperature, but a precise combination of factors that includes a star of the right type and stability, a planet in the right orbital position, a large moon to stabilize axial tilt, plate tectonics to recycle carbon and regulate the climate, a giant planet like Jupiter in the outer system to deflect comets and asteroids, the right mix of heavy elements in the crust, a magnetic field strong enough to deflect solar wind, a long period of relative stability without too many extinction-level events, and probably other factors we haven't fully characterized. On Earth, all of these conditions are met, but the argument is that each condition narrows the field substantially. What if the probability of any one of these factors is 1 in 10, and there are 10 such factors, the probability of all 10 occurring together is 1 in 10 billion. In a galaxy of 400 billion stars, that gives you a few dozen planets with the right conditions for complex life. A few dozen, not billions. The rare Earth hypothesis is scientifically serious and testable, at least in principle, as we characterize more exoplanets and their environments in greater detail. It's been criticized on various grounds. Some of its specific factors are contested, and the anthropic principle complicates the inference from Earth's conditions to the universal requirements for life. But it represents a coherent, evidence-based path to explaining the Fermi Paradox without requiring future catastrophe. Let me go through the specific factors Ward and Brownlee identified, because the cumulative weight of them is more convincing than any single factor alone. The galactic habitable zone is the first. Not every part of the Milky Way is equally hospitable to complex life. The center of the galaxy is crowded with stars, intense radiation, frequent supernovae, and proximity to the supermassive black hole Sagittarius A, which has periodic episodes of violent activity. Stars in the outer disk of the galaxy, far from the center, tend to be metal poor, formed from gas that has not been enriched by many generations of stellar nucleosynthesis, and therefore lacking the heavy elements needed for rocky planets and biochemistry. The galactic habitable zone is a ring at intermediate galactic radii, far enough from the center to avoid the most intense radiation and gravitational disruption, close enough to the center to have sufficient heavy elements. The Earth orbits at about 26,000 light-years from the galactic center, squarely within the estimated galactic habitable zone. That may not be coincidence. It may be selection. Stellar type matters enormously. Our Sun is a G-type main sequence star, a yellow dwarf, relatively stable, with a lifespan of about 10 billion years. G-type stars are not the most common type. Red dwarfs are, by a wide margin, comprising about 70% of all stars. But red dwarfs present problems for life. They are dim, requiring planets to orbit very close to receive enough heat to maintain liquid water. At those close distances, planets are likely tidally locked, one face permanently toward the star, one face permanently away. The tidal locking creates extreme temperature gradients, violent atmospheric circulation, and a permanent dark hemisphere that may develop permanent ice coverage and then reflects heat and drives the rest of the planet toward a frozen state. Red dwarfs also flare frequently and intensely during their early billions of years, bombarding close-orbiting planets with ultraviolet and X-ray radiation. Whether life can survive and thrive in this environment is debated. Some researchers argue that life could adapt. Others argue the combination of tidal locking and intense stellar activity makes red dwarf planets poor candidates for complex life, even if microbial life might survive. K-type stars, somewhat cooler and dimmer than our Sun, more stable than red dwarfs, and extremely long-lived, may actually be better hosts for life than either G or M stars. They are stable, not prone to intense flaring, and allow planets to orbit at comfortable distances without tidal locking. They are increasingly the focus of biosignature search programs. The large moon is the factor that most people find surprising when they first encounter it. Earth's moon is unusually large relative to its host planet. The Moon-to-Earth mass ratio is the largest of any planet-satellite system in the solar system, by a significant margin. The Moon's gravitational influence stabilizes Earth's axial tilt. Without the Moon, Earth's axis would wobble chaotically over timescales of tens of millions of years, swinging from near-zero tilt, a world with almost no seasons, to very high tilt, a world with extreme seasons, with the poles receiving more sunlight than the equator during summer. This chaotic variation in axial tilt would drive wild climate swings, potentially disrupting the stable conditions that allowed complex life to evolve over hundreds of millions of years. Mars, which has no large moon, has undergone dramatic axial variations in the past, contributing to climate instability. Earth, stabilized by its large moon, has maintained a relatively stable tilt for hundreds of millions of years, long enough for evolution to produce the complexity we see in the fossil record. How did Earth get such a large moon? The leading hypothesis, the giant impact hypothesis, now supported by multiple lines of evidence, including isotopic analysis of lunar rocks returned by Apollo, is that roughly 4.5 billion years ago, a Mars-sized protoplanet named Theia struck the proto-Earth in a glancing blow. The impact was catastrophic. The energy released was sufficient to vaporize much of both bodies. The debris from the impact, flung into orbit, coalesced within a geological eye blink into the Moon. This event was essentially a random accident of the early solar system's chaotic dynamics. Other planetary systems will have collisions of their own, but whether they produce large stabilizing moons around potentially habitable planets is a matter of geometry and timing that may not be common. Jupiter's role as a gravitational shield is another factor. Jupiter is massive enough, 318 Earth masses, that its gravity substantially perturbs the orbits of small bodies in the outer solar system. Over time, this has acted to clear the solar system of many potential impactors, either ejecting comets into interstellar space or pulling them into Jupiter itself. The collision rate on Earth is lower than it would be without Jupiter, and a lower collision rate means fewer mass extinctions, more evolutionary continuity, more time for complexity to develop. The Late Heavy Bombardment, a period roughly 4 billion years ago, when the inner solar system was struck by a high flux of impactors, possibly triggered by the gravitational migration of the giant planets, was destructive, but it apparently did not sterilize Earth, and after it ended, the impact rate dropped to a level that allowed complex life to eventually emerge. Whether most planetary systems with habitable zone rocky planets also have Jupiter mass outer planets to provide this shielding is not yet known. Early data from planet-finding surveys suggested that Jupiter-mass planets in Jupiter-like orbits are relatively uncommon. The implications of this for the prevalence of complex life are debated. Plate tectonics, the movement of Earth's crystal plates, driven by heat from the interior, plays a role that is subtle but possibly crucial. Plate tectonics recycles carbon. When carbon dioxide dissolves in rainwater and forms carbonic acid, which weathers silicate rocks and carries carbonates into the ocean, and when ocean plates subduct under continental plates and carry that carbonate material into the mantle, where it is eventually degassed back into the atmosphere through volcanoes, this carbon silicate cycle regulates the long-term concentration of CO2 in the atmosphere and acts as a thermostat for Earth's climate. Without, I can't see some kind of CO2 without being recovered, or it would be depleted, potentially producing runaway glaciation like snowball Earth events. The carbon silicate cycle has kept Earth's climate within the range required for liquid water for billions of years, even as the sun has slowly brightened by about 30% since Earth's formation. Not all rocky planets have active plate tectonics. Whether Earth's tectonic activity is typical or unusual for a planet of its size, composition, and age is an active research question. The cumulative effect of all these factors, galactic position, stellar type, large moon, outer gas giant shield, plate tectonics, magnetic field, the specific timing of the evolution of complexity is to make Earth's habitability look less like an inevitable outcome of having a rocky planet in the habitable zone, and more like a product of a specific contingent history that may not be widely replicated. This doesn't mean Earth is unique, with 40 billion potentially habitable planets in the galaxy. Even 1 in a million odds produce 40,000 Earth-like worlds. But it may mean the number of truly Earth-like worlds, places where complex animal life has had billions of years to evolve, is far smaller than the simple count of habitable zone rocky planets would suggest. The exoplanet data from the past decade is beginning to constrain these arguments. The TRAPPIST-1 system, with its 7 roughly Earth-sized planets in tight orbits around a red dwarf, has become a test case for the red dwarf habitability question. The Kepler and TESS missions have characterized the frequency of planets of different sizes and orbital periods around different types of stars, giving us statistical pictures of what planetary systems look like. The biosignature search programs building on Webb and planned for future missions will, over the coming decades, start to tell us whether Earth-like atmospheres are common or rare. Every piece of new data narrows the uncertainty range. The honest summary of where the rare Earth hypothesis stands today is plausible but not proven. Some of its specific claims have been weakened by new data. The discovery of diverse planetary systems has expanded our understanding of what conditions can produce rocky worlds. And extremophile biology has expanded our understanding of what conditions life can tolerate. But the core argument that the combination of factors required for complex animal life may be significantly less common than the raw count of habitable zone planets suggests remains scientifically credible. AMD. It is not the consensus view because there is no consensus view. It is one of several serious hypotheses that fit the available data. We passed through many small filters. We are genuinely rare, genuinely special in a measurable astrophysical sense. Not unique necessarily, there might be a few dozen other complex civilizations in the galaxy, but rare enough that the silence makes sense without invoking our eventual destruction. There's another explanation that takes a completely different approach: the simulation hypothesis. If we are living in a computational simulation, if the universe, as we experience it, is a model running on some substrate we don't have access to, then the Fermi Paradox dissolves. The simulators didn't populate their simulation with alien civilizations we could contact. Either because that's computationally expensive, or because the point of the simulation is to study something about isolated civilizations, or because the simulators made a choice we can't know. This isn't falsifiable in any obvious way, and, as an explanation for the Fermi Paradox, it has the unsatisfying quality of explaining everything by appealing to something outside the framework of observation. But it's been taken seriously by serious people, and intellectual completeness requires mentioning it. There is the berserker hypothesis, proposed in various forms since the 1980s, which suggests that a predatory civilization, or more likely a predatory artificial intelligence, left running after its creators died, has been systematically eliminating or suppressing technological civilizations as they emerge. The galaxy is quiet because something is enforcing the silence. This is the darkest explanation on the list. It is also the one that, if true, we are about to announce ourselves to in the loudest possible way, because our radio transmissions have been expanding outward at the speed of light for over 100 years and are now more than 100 light years from Earth. I don't think this is the most likely explanation, but it is not zero. And if it were true, the advice it implies is, be very quiet and hope you haven't already been noticed. The transcension hypothesis, proposed by futurist John Smart, takes a different view. Maybe advanced civilizations don't expand outward into the galaxy. Maybe they expand inward, into smaller and smaller scales of computation, into virtual realities, into the miniaturization of minds and societies. A civilization that can simulate rich inner universes with less energy and matter than it would cost to colonize stars might choose to do so. From outside, such a civilization would be undetectable, not because it's hiding, but because it has moved beyond the physical scale at which we're looking. This is an optimistic explanation, in that it doesn't require extinction. But it's almost unfalsifiable, and its plausibility depends heavily on whether inner space is actually as interesting as outer space for an arbitrarily advanced mind, which we can't know. Let me spend a moment on the search for extraterrestrial intelligence, SETI, because understanding what we've actually done gives important context for evaluating the silence. Project Ozma in 1960 was the first systematic SETI search. Frank Drake pointed a radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened at 1420 MHz for 2 months. Nothing. This was not a comprehensive search. It was a proof of concept. But it established the methodology and, more importantly, it established the culture of SETI, serious scientists, using real instruments, asking a real scientific question. Drake followed that first search with something more lasting, the Drake equation, a formula he sketched on a blackboard at a 1961 meeting in Green Bank, West Virginia, the first scientific gathering dedicated entirely to to the question of extraterrestrial intelligence. The equation wasn't designed to give an answer. It was designed to organize ignorance, to clarify which questions needed answering before the big question could be addressed. The equation multiplies together a chain of factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life emerges, the fraction where intelligence evolves, the fraction of intelligent species that develop detectable technology, and the average lifespan of a technological civilization. Plug in optimistic numbers and you get millions of civilizations. Plug in pessimistic numbers and you get fewer than one. The equation doesn't solve the Fermi Paradox. It describes its shape. It tells you which uncertainties matter most. The one that matters most, the one that dominates the result, is the last term, the lifespan, L. How long does a technological civilization survive after it develops radio communication? If the average is a few hundred years, the galaxy is essentially empty at any given moment, even if civilizations arise constantly. If the average is millions of years, the galaxy should be full of detectable signals. Everything rides on L. And L is the one term we cannot estimate from astronomical data. We can only estimate it from what we know about ourselves. And what we know about ourselves, about how we handle the technologies we've developed, about how we coordinate collective responses to collective risks, is genuinely uncertain. Since Project Ozma, SETI has expanded in scope, funding, and technological sophistication through a long history of programs with varying levels of institutional support. The Ohio State University's Big Ear Telescope conducted the most sustained early SETI search, running continuously from 1973 until 1995, when the telescope was demolished to make way for a golf course expansion, which remains one of the more absurd footnotes in the history of science. It was Big Ear that detected the WOW signal in August 1977. NASA funded SETI research intermittently, launching the High-Resolution Microwave Survey in 1992, the most ambitious SETI project attempted at that point. Designed to survey 10 million frequencies across thousands of stars using upgraded hardware at the Arecibo Observatory in Puerto Rico and the Goldstone Deep Space Communications Complex in California. Congress defunded it in 1993, 1 year into the program, with Senator Richard Bryan of Nevada calling it a waste of money on a search for little green men. The cancellation was widely criticized in the scientific community. SETI research moved into the private sector, where it has primarily lived since. The Allen Telescope Array, a dedicated SETI instrument built through a partnership between the SETI Institute and the University of California, Berkeley, with initial funding from Microsoft co-founder Paul Allen, came online in 2007. It consists of 42 small dishes operating as an interferometer, many smaller dishes linked electronically to function as a single larger telescope, capable of monitoring multiple stars simultaneously across a wide frequency range. It remains the only telescope built specifically for SETI rather than adapted from other astronomical purposes. Breakthrough. Listen, launched in 2015 with a $100 million commitment, represents the most serious and best resourced SETI effort in history. The program uses dedicated time on the Green Bank Telescope in West Virginia and the Meerkat Array in South Africa, and analyzes its data with machine learning systems that can process billions of channels simultaneously and flag candidates for human review. In its first years of operation, Breakthrough Listen reanalyzed archival data from multiple telescopes and identified dozens of signal candidates that had been missed by earlier, less sophisticated analysis pipelines. All of them, when investigated, turned out to be terrestrial interference. But the discovery that machine learning could find candidates human analysts had missed raised a possibility that genuine signals might be hiding in data we've already collected, waiting for better tools to surface them. The program has also made methodological advances that go beyond the traditional radio search. Breakthrough Listen has begun conducting optical SETI, searching for laser pulses from distant star systems, which would be another logical communication medium for an advanced civilization. Lasers can be collimated into extremely tight beams, allowing enormous energy to be concentrated into a small, solid angle. A civilization beaming a laser pulse at Earth from a nearby star system could, in principle, be detected with existing astronomical instruments during the brief moment the beam sweeps past us. No confirmed detections. Since then, SETI has expanded considerably. The Allen Telescope Array in California, a network of small dishes designed specifically for SETI observations, can monitor multiple stars simultaneously across a wide range of frequencies. Breakthrough Listen, funded by billionaire Yuri Milner with $100 million and announced in 2015, is the most comprehensive SETI program ever undertaken. It uses the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia, two of the largest and most sensitive radio telescopes on Earth, to systematically survey the 1 million nearest stars, the 100 nearest galaxies, and the central plane of the Milky Way. It monitors billions of radio channels simultaneously and applies machine learning to identify anomalous signals in the data. The results to date? Nothing confirmed. The Breakthrough Listen team has published multiple papers describing candidate signals that were investigated and ruled out. In 2020, a signal designated BLC1, Breakthrough Listen Candidate 1, was detected at 982 MHz, appearing to come from the direction of Proxima Centauri, the nearest star to the Sun at just over 4 light-years away. The signal was narrowband, consistent with an artificial rather than natural origin. It showed a frequency drift consistent with a planet moving relative to Earth. It was the kind of signal the program was designed to find. For several months, a small team investigated it carefully without making it public. In early 2021, the investigation was published. BLC-1 was almost certainly terrestrial interference. The signal appeared during observations of multiple targets, not just Proxima Centauri. Its frequency characteristics were inconsistent with a planetary origin. It was something on or near Earth, likely a satellite or ground-based transmitter, that appeared in the data when the telescope was pointed in that direction. Several searches for Dyson spheres have been conducted using infrared survey data, most extensively by Penn State astronomer Jason Wright and collaborators. The search examined data from the WISE and 2 mass infrared sky surveys, looking for stars with the characteristic infrared excess that a Dyson sphere would produce. The searches found candidates, a few hundred stars with anomalous infrared signatures, but follow-up investigation attributed all of them to natural sources: debris disks, companion stars, dust clouds. No confirmed Dyson spheres. The Tabby star case, formerly KIC 8,462,852, a star about 1,500 light-month deviled by citizen scientists analyzing Kepler data in 2015, generated enormous attention precisely because its behavior seemed initially inexplicable by natural means. The star showed irregular, aperiodic dips in brightness, some of them as large as 22%, far larger than any planetary transit could produce, and with shapes inconsistent with any known astronomical object. The hypothesis that a partially constructed Dyson sphere might be blocking the light was floated seriously by researchers, including Wright. Subsequent follow-up observations, including spectroscopic analysis of the dimming events, found that the dimming is wavelength dependent in a way consistent with fine dust particles rather than a solid structure. The current consensus is that the dimming is caused by a swarm of cometary debris or the aftermath of a planetary collision. Extraordinary by normal astronomical standards, but natural. Tabby's star is an example of the universe being stranger than our models, not of alien construction. One more candidate worth discussing: fast radio bursts. FRBs are millisecond-long pulses of radio energy with extraordinary brightness, detected coming from distant galaxies. When first discovered in 2007, they were deeply puzzling. Nothing in the known catalogue of astrophysical objects seemed capable of producing them. Their discovery triggered a period of genuine excitement in certain corners of the SETI community. In 2017, Harvard astrophysicist Avi Loeb published a paper arguing that FRBs could be consistent with the leakage from extragalactic alien civilization radio beams used to accelerate interstellar spacecraft, the same technology we have theorized ourselves with the Breakthrough Starshot project. The energies and characteristics of FRBs, Loeb argued, fit that interpretation. The mainstream view is that FRBs are produced by magnetars, neutron stars with extraordinarily strong magnetic fields, a model that was confirmed in 2020 when an FRB was detected from a known magnetar within our own galaxy. Most FRBs are almost certainly natural, but most is doing some work in that sentence. And the 2020 galactic FRB, while dramatic confirmation of the magnetar model, was also noticeably weaker than extragalactic FRBs, raising the question of whether the energetics are fully explained. This is the state of the field. Null results, intriguing candidates, and one unexplained anomaly from 1977 that we've never been able to fully rule in or rule out. Now, I want to address something that often gets glossed over in discussions of the Fermi Paradox: the role of time. The universe is 13.8 billion years old. The Milky Way formed about 13.6 billion years ago. The first generation of stars in the Milky Way were massive, burnt fast, and died as supernovae within a few million years. They seeded the galaxy with the first heavy elements: carbon, oxygen, nitrogen, iron, the building blocks of rocky planets and biochemistry. Second and third generation stars formed from this enriched gas. Our Sun is approximately third generation. It contains heavy elements from multiple prior stellar generations. But here's an important consideration which changes the picture somewhat. The very early universe may not have been hospitable to complex life, even when stars and planets existed, because the galaxy was a more violent place. Supernovae, gamma-ray bursts, and the active galactic nucleus at the center of the Milky Way were all more intense in the early universe. High-energy radiation events could sterilize planetary surfaces across large volumes of space. The habitable zone for complex life may not just be a spatial concept, a region around a star, but also a temporal one, a period in galactic history when the environment is calm enough to allow complex organisms to survive long enough to evolve intelligence. Some researchers have argued that we may be among the first civilizations in the Milky Way, not because life is rare, but because the galaxy only recently, in the last billion years or so, entered a relatively stable phase where complex life can persist long enough to become technological. On this view, we're not looking for others who came before us in the early galaxy. We're looking for contemporaries. And if the habitable period of the galaxy only began a billion years ago, a billion years is not as much time as it sounds. It's only enough for life that emerged quickly to have reached our stage. The filter, in this view, is temporal. We are near the beginning of the era of intelligent life, not in the middle of a galaxy full of civilizations that have had much more time than we have. This is an optimistic interpretation, and it has some scientific support. It is not, however, the consensus view, and it doesn't remove the deep uncertainty at the heart of this question. Let me tell you about the thing that actually keeps serious people up at night when they think about this problem: the asymmetry of evidence. When we look at the history of life on Earth, we see multiple examples of independent evolution of certain traits. Eyes evolved many times in different lineages. Flight evolved multiple times. Complex brains evolved in multiple lineages. This is convergent evolution. When a trait is useful, evolution finds it from different starting points. This suggests that certain outcomes are in some sense attractors, solutions that the evolutionary process converges on, given enough time and the right conditions. Intelligence looks like it might be one of those attractors. It confers such enormous survival and reproductive advantages, but the evolutionary pressure toward it, once a lineage has the basic cognitive architecture, seems strong. On Earth, we have dolphins, elephants, great apes, corvids, and octopuses, multiple independent lineages that have evolved unusually high cognitive capabilities. The trend toward greater intelligence in many lineages over the past few 100 million years suggests that if you give evolution enough time on a planet with complex life, it will tend to produce something smart. But the Fermi Paradox is telling us that smart is not enough, or that smart combined with technology is not stable. Because if smart species with technology routinely colonize their galaxies, we would see it. The galaxy colonizing step is the one that almost never happens. Not the getting smart step, not the building radio step, the surviving long enough to become galaxy spanning step. That is the most specific, most constrained thing the Fermi Paradox actually tells us. It doesn't tell us life is rare. It doesn't even tell us intelligence is rare. It tells us that technological civilizations at the level of radio communication almost never survive to become interstellar civilizations. The window between can build a radio and has spread across the stars is apparently very narrow. And we are in that window, right now. I don't know how to make that less uncomfortable, because I don't think it should be made less uncomfortable. The appropriate response to finding out that you're in the most dangerous period of your civilization's existence, the bottleneck, the eye of the needle, is not to find reasons not to believe it. The appropriate response is to take it seriously and act accordingly. What would acting accordingly look like? It would look like treating the risks of nuclear war, climate change, artificial intelligence, and engineered biology as the existential level threats they potentially are, not as policy problems to be managed incrementally between election cycles, but as civilizational challenges that require the kind of sustained, coordinated, adequately resourced response we have historically only achieved during wars. It would look like building international institutions with real authority and real enforcement capacity, not because we believe in global government as an ideology, but because the failure modes of uncoordinated national actors facing existential risks are unacceptable. It would look like developing space-based backup populations, not as a luxury project, but as an insurance policy. It would look like taking seriously the possibility that we might be the first civilization to successfully pass through the bottleneck, and that whether we do depends entirely on decisions made by people alive today. Here is where I want to land, because this deserves more than a warning. The Fermi Paradox is not just a question about aliens, it is a question about us. The most important thing it tells us is that the universe is hard in ways we don't fully understand yet. That the pathway from chemistry to civilization is blocked somewhere by something more reliably than we would have expected from first principles. And that we have the extraordinary, unprecedented, terrifying privilege of being on that pathway right now, at the moment that matters. If the filter is behind us, if we are the rare exception that got through, then the galaxy is available. Not to conquer, not to exploit, but to explore, to fill with the kind of complexity and beauty that apparently almost never exists. That would be an astonishing thing to be, the first, the lucky ones who made it to the other side, the species that survived what almost nothing survives. If the filter is ahead of us, if we are one of a long line of civilizations that reached this moment and almost all of them failed, then the most meaningful thing we can do is be the exception. Not out of arrogance, not because we're special, but because there is no one else to do it. The galaxy has been waiting for billions of years. It may be waiting for us specifically, not because we are chosen, but because we are here. And here is where the choice happens. Either way, the silence is not an invitation to give up. It is an invitation to understand what we're up against, to take the universe seriously, to be honest about the risks we've created, and to make different choices than whatever came before us. The stars are quiet. They've been quiet for a long time. The question is whether that quietness ends with us, or because of us. The answer is not written yet.